All right, welcome everyone to this fifth video, I believe. In chapter 17 here, we're going to talk more about titrations. In this video, we're going to talk about weak acid, strong base, weak base, strong acid, polyprotic acid titrations, things like that. So kind of other types of titrations we might deal with, okay? So let's first consider a weak acid, strong base titration, right? So if I think of initially, right, I just have my weak acid, let's say it's hydrofluoric acid, right? In solution, that hydrofluoric acid establishes equilibrium, right? In that solution, form H plus F minus, right? And that's all I got in solution initially, okay? Now, and right in that solution, it's mainly HF, very small concentrations of H plus and F minus, right? Okay. Now, if I add some strong base to that solution, that base will react with HF, right? With the addition of strong base, I'll have HF reacting with, say, sodium hydroxide, right, to form NaF plus H2O, right? That's the reaction that's going to occur, right? And that NaF, right, sodium is just a spectator ion, right? This is really just forming F minus in solution, right? And so then when I've reacted some of my weak acid to form a weak base, right, I now have a solution that contains a weak acid with its conjugate base, and I've formed a buffer solution, okay, right? So this now is an equilibrium solution, that's a buffer solution. I can just use the Henderson-Hasselbalch equation to find the pH, right? At any point so far during this partial neutralization phase, right? So this kind of first phase here, right? Actually, all three of these points, right, are all talking about when I have partial neutralization, right? Right, partial neutralization, right? Okay, now when you reach halfway to the equivalence point, right? So the equivalence point again is when I've added equal amounts of acid and base in solution. Halfway to that point, you will have a buffer solution in which the pH will equal the pKa, okay? And then once you've reached the equivalence point, right, you've consumed all of your weak acid, and now you've formed a weak base in solution. So now, at the equivalence point, I got F minus floating around in solution, right? Well, that F minus, right, will react with water to form HF plus OH minus, which will make the solution basic, right? So the equivalence point is no longer going to be at a pH of 7 for a weak acid, strong base. So let's look at what this looks like, what these titration curves look like, right? So for a weak acid being titrated with a strong base, again, I start off with an acidic solution still, because I have a weak acid, right? I then get a buffer solution, right, where the pH is increasing with the addition of the strong base, okay, but very gradually, okay, halfway to that equivalence point, right? The equivalence point is at 25 or 50 milliliters, so halfway to that is 25 milliliters, right? At halfway through that, the pH is equal to the pKa of that weak acid, okay? And then at equivalence point, I now have a pH, right, that is greater than 7, okay? Because now I just have a weak base in solution, okay, right? Right at equivalence point, I now have just my weak base, my acetate ions in the solution. Those acetate ions will make the solution a little bit basic, right? And so this solution will be now basic. And then once I start adding more and more sodium hydroxide, right, I'm then basically just diluting the sodium hydroxide. That strong base is going to control the pH, right, and I just form a very basic solution, okay? Now some notes about this, okay, these weak acid, strong base titration curves, right? right? So here we have a bunch of plots here where I have different values of Ka, right? Recall that the larger the Ka, the stronger the acid, right? So the strength of the acid is increasing as we go down, right? Right, so you see the stronger the acid, right? The lower the initial pH, right? And then the weaker the acid, the higher the pH will be at equivalence point, right? Because the weaker the acid, the stronger the conjugate base is going to be, right? So for this Ka of 10 to the minus 8, right? The conjugate base formed at the equivalence point, right, is going to be a much stronger base than the conjugate base that's formed when I have a Ka of 10 to the minus 2, right? And so if I have a stronger conjugate base, right, that's going to form a more basic solution, so it's going to have a much higher pH, okay? Right, and so, right, and so this is kind of the trends that you'd see if you were to do a titration curve of different acids of different acidic strengths, okay? So for a strong acid with a weak base, it's basically the same type of thing, right? Now at equivalence point, your pH is going to be less than 7, okay? At equivalence point, you're going to be left, right, at equivalence point, right, you're going to react your strong acid with all your strong base, and you're just going to be left with NH4 plus in solution, right? That NH4 plus is going to react with water, form its conjugate base, right? And H3O plus, right? And so this is going to make the solution acidic. So this is going to have a pH less than 7, okay? And that's the same, right, for, so that's the exact opposite kind of, right, of a weak base with a strong, or sorry, a weak acid with a strong base, right, is the opposite thing, right? Where it's a pH greater than 7, in this case you have a pH less than 7 when you have a weak base being titrated with a strong acid, okay? But you also, and under partial neutralization, right, before you reach that equivalence point, you're going to form a buffer solution, okay? Right? And then after the equivalence point, you're just going to be basically adding strong acid, and it's going to be a very acidic solution, okay? Right? Now, titrations of polyprotic acids look like any other kind of type of titration. It's just you got multiple equivalence points for each acidic proton on your acid, right? So here, our acid is H3PO3, okay? So I have 3 protons that I can titrate off, right? And so I'm going to have an equivalence point for each proton that I've removed, right? So the first equivalence point is at 50 milliliters, second equivalence point is going to be at 100 milliliters, and then there's going to be a third equivalence point, right, at 150 milliliters, right? Right, and so, right, the number of equivalence points is equal to the number of acidic protons that you have, right? And notice that the pH at equivalence point is increasing for every equivalence point, right? Okay. But yeah, basically, right, the titration of some polyprotic acid looks like titration of like a weak acid with a strong base. It's just that you then keep going and have multiple equivalence points, depending on how many acidic protons there are in your acid. Okay. Right, and so how you work these things in the labs is, again, often you use some type of indicator to let you know when you've reached equivalence point. Okay. Right, and so, like, let's say I have this, indigo type indicator, right, where the reactants are a red color, products are a yellow color, right? So, right, in an acidic solution, right, what would the color be? Well, in an acidic solution, right, I have a bunch of H+, so I've effectively added a bunch of protons, okay? That's going to shift the equilibrium to the left, and so this is going to be red in acidic solution, right? In basic solution, it's the opposite, right? I've now removed a bunch of H+ ions, and this equilibrium is going to want to reestablish itself and shift to the right. And so in basic solution, this is going to be yellow, right? And then in between might be kind of some sort of orangish color or something like that, right? Kind of just depends, right? That's where you are in between, okay? But it will shift from red to yellow, maybe look a little orange at some point, right? Somewhere in between, okay? Right? So again, titrations in lab work often by using these indicators, and basically the indicators, right, is when you've reached this equivalence point is when you've reached kind of the end point where the color change of the indicator occurs. At least that's the hope, right? You want to pick the indicator that does that, right? So to do that, you need to make sure your indicators have their pKa roughly within plus or minus 1 pH of the pH that you're trying to like assume your equivalence point is at, right? So again, if you know you're titrating a strong acid with a strong base, you want an indicator that has a pKa around 7, right? But if you're titrating a weak acid with a strong base, then maybe you're going to want an indicator that has a pKa greater than 7, because you know that at equivalence point, your pH is going to be greater than 7, right? And so that does it for titrations, okay? Talked about different types of titrations that one can do for these acid-base titrations, right? And in class, we'll go over plenty of examples of these things as well.